Alright, so the second question that I find it very interesting when I'm taking the 2022 O-level physics, right, is this question from paper 2. So, okay, so let's take a look at this question together. So the critical angle for light, right, traveling from glass into air is 42 degrees. So this is the critical angle, right? Okay, so we have this figure showing a diverging beam of light from a light source, L striking the boundary between the glass and air. So the light is actually traveling from more dense to less dense medium. So ray A and B forms the edges of the diverging beam in the glass. Okay, part I state and explain which ray A or B emerges into the air. Okay, so for this question, so let's look at this. Let's look at ray A first. Okay, ray A, you must always draw a normal, and of course the angle of incident. Okay, so the angle of incident is 30 degree. Then after that, you look at ray B. Ray B, you draw a normal. So let me just draw again. So you draw the normal, right? You will notice one thing is that, the angle of incidence is 60 degree. So if you compare 30 and 60, right, which one is less than the critical angle? Definitely is ray A. So if you are less than critical angle for ray A, the angle of incidence is less than the critical angle, right, you will emerge out of the glass into the air. So you will emerge like this. So for example, you will bend away from the normal. Okay, what about ray B? Ray B, actually, you will undergo something called a TIR, because for B, your angle of incidence, which is 60 degree, is already more than the critical angle. So TIR will occur. So you will become like this. Right, so of course, how do I explain? State and explain, right? So state is the ray, so it's ray A. So why do ray A emerge into the air? Because you must say that, the angle of incident in the glass is 30 degree, which is lesser than the critical angle of maybe you can just elaborate like 40 degree, and this will cause the ray A to exit the glass and bend away from the normal. Okay, so this is a 2 marks question. So the first mark is actually this part. The second mark is actually explain why ray A emerges. So the second mark is this part. Alright. Okay, so part 2 is another very weird question. Okay, so part 2, only part of the beam emerges between A and B. Right, I mean between A and B emerges into the air. So on figure 5.1, bullet point 1, right? So draw a line from L that separate the part of the beam that emerges into air from the part that does not. So when I first look at this question, I didn't understand what they want. So of course, I skip the question first, then after that, I come back. So after that, finally, I understand what they want. So, okay, so if you look at this, they actually want us to draw a line. Just one line. So I just, maybe I just erase something first. Okay, if you look at this picture, they want us to draw a line that separate the light that emerges out and the light that doesn't emerges out. Okay, so you just roughly draw this part. Okay, so you just roughly draw this line. So you just label it as L. So anything that is before this blue color line, light will emerge. Right? Anything that is beyond the blue color line, light will not emerge. So that's actually what they want. Right? Okay, then the bullet point to draw rays that emerge into the air to show the edges of the beam into the air. So of course you see draw rays, right? You cannot just draw one ray. You must draw a few rays, right? Okay, so let's draw a few rays to answer this question. Okay, so first thing, I draw maybe I draw 3 rays. So maybe first ray I draw the ray A. So you draw bend away. Okay, then you draw another maybe I call it this ray. Okay, this ray you draw okay, the purple ray, you draw another ray, but you must make sure you bend further away from the normal. Right? After that, you can also draw one more ray. So you draw one more ray, you can okay, I draw, maybe use green color. Okay, I draw one more ray. I draw normal. You bend further away, okay, from the so-called normal. Yeah, so these are the 2 points. Right, so okay. Okay, so let's move on to question B. So many glass optical fiber are covered with cladding, right, as shown. Okay, so the refractive index of the cladding must be less than of the glass but more than that of the air. State, explain how the speed of light in the cladding compares with the speed of light in the glass fiber. Okay, so they already give us the information already. They say that, my glass optical fiber, right, has a greater refractive index compared to the cladding. So cladding must have less optical density. So why must that be? Why must I do that? Because always remember, what are the 2 criteria to undergo total internal reflection? So the 2 criteria is actually, of course, the angle of incidence must be more than the critical angle. So for example, right, I have this light ray enter in this particular direction. So I draw a normal. So the angle of incidence here must be greater than the critical angle to undergo your total internal reflection. So that is the first criteria. Second criteria is actually to make sure that the light actually travel from more dense to less dense medium. So you must make sure that my light travel from more dense to less dense, which is true in the optical fiber. If not, total internal reflection will never occur. Okay, so they say, okay, stay and explain how the speed of light in cladding compared to the speed of light in the glass fiber. Since we know that in the glass fiber, right, or glass optical fiber, it is more dense. More dense means the speed of light must be lesser. Alright. Then for the cladding, since the cladding has less optical density, so the speed of light will be greater. So you just explain this manner. So the speed of light in glass is smaller than the speed of light in cladding. Okay, so of course it's 1 mark lah. So I try to explain, because since glass has a greater the refractive index is greater than the cladding refractive index. Okay, yeah, so that's the idea. Okay, so for part 2, the last part, this one is a very very tough question. So state and explain whether the critical angle for light traveling from glass into the cladding is equal, larger, or smaller than 42. 2 marks. Okay, so first thing first, to answer this question, we must go back to the critical angle formula. So always remember, the critical angle formula is sine C is equal to 1 over n. So for this formula, this is only applicable to maybe glass and air boundary. So for example, if I give you maybe a glass here, and I give you a air here, right? So to calculate the critical angle in the glass, I can use this formula. Alright, so if you look at this 1 over n, the 1 actually is the refractive index of air. Then the n at the bottom here is actually the refractive index of the glass. Okay, so that is the sine c equal to 1 over n. Okay, so what about if let's just say I have a cladding and a glass boundary, so can I use sine c equal to 1 over n? So the answer is no. So for this, we must use something like sine c equal to something over something. Okay, so what is the top? What is the thing that I should write at the top? Is the refractive index of cladding. Then after that, the bottom, you write the refractive index of glass. Okay, Yeah, so as a rule of thumb, if you don't understand this is derived from the Snell's law. But if you don't understand Snell's law, never mind. You always remember the top will be the less dense medium. The bottom will be the more dense medium. It's always the case one. So sin C equal to the refractive index of less dense medium over the refractive index of more dense medium. Okay, so for this, you can see, right, sin C equal to 1 is refractive index of cladding divided by refractive index of glass. So first thing first, if you look at this second equation that I give you right here, so how do the critical angle compare with the very first case here? So the very first case, the critical angle right here is equal to 42 degrees. So what about the second case? The second case, if you use a bit of maths, so sin C equal to n of maybe I put cladding divided by n of maybe glass. So you can see that this n here is greater than the 1 here. So of course I just put higher. So if you sine inverse of this whole thing here, your critical angle will be definitely more than 42 degrees. Okay, if you don't believe, I can calculate for you. So for example, sin C equal to cladding over glass. So for example, let me just put down some numbers. Okay, cladding, maybe I just put 1.4. The refractive index of cladding is 1.4. For refractive index of glass, maybe I put 1.52. Alright, so let's calculate what is the critical angle. So for critical angle wise, you can actually put sine inverse 1.4 divided by 1.52. So you will get roughly 67.1 degree. So you can see that it's already more than your 42 degree already. Okay, so next, maybe I just calculate the glass and the air critical angle. So sin C is equal to 1, right? So this one is actually the refractive index of air divided by glass. Okay, glass roughly is 1.52 lah. 1.52. So you just calculate what is the critical angle here. So sine inverse 1 divided by 1.52, you'll get roughly 41.1 degree. So you can see, right, for the cladding and glass, the critical angle will be greater. So how do I explain this? So first, right, state. You just say that the critical angle will be greater than 42 degree. Then second, mark, right. This one is a difficult one. So you just say that, since sine C equal to n divided by n, so n is cladding, then this is glass. So since the refractive index of cladding is high, right, means that sine C is greater. So since sine C is greater, the critical angle will be greater. Alright, so it's something like math like that. So for example, right, cladding here, I write high, so the whole thing here will be high. Since whole thing here is high, critical angle will be greater. So that's how you do this 2022 O-level question.